This is lecture number 17 of course MET14 Fluid Mechanics 2, and this is the second lecture of this week. We have already talked about basic potential flows, in which uniform flow we have done, source and sink flow we have done, and the vortex flow we have done. So these, and we have worked out their corresponding stream functions and velocity potential functions. In today's lecture, we are going to do the superposition of the basic potential flows. So these basic potential flows, when superimposed together, add them together, so there would be a resulting flow pattern. That is what we are going to study today. First, we will look at visually, and then we will go into the mathematical description of the resultant flows. Doublet is the first thing we will go today, and then we will go into the half body, so let's talk about superposition of the potential flows. You have any streamline in an inviscid flow can be considered as a solid body. As you see, you have a bunch of streamlines, and since the streamlines are such that actually follow certain path, and the lines are going parallel to each other, so you don't see that there are no two streamlines which are crossing each other or which are intersecting each other. So when we see these streamlines, since there is no flow taking place at the boundary of the streamline, so there is no cross flow takes place. So because the dominant direction of the flow is in the streamline direction, so there is no cross flow takes place, and it is a peculiar feature for inviscid flow, where viscosity effects are not considered, and then that streamline would act as a solid body. So this is just look at the superposition principle. So when I say superposition, it means algebraically you are going to add them together. So if you have two functions, if you have superimposed them, you just simply add them together. Okay, let's look at this uniform flow case. We have already worked out the expression for uniform flow. Uniform flow means it is all streamlines are parallel to each other, and they are moving in a particular direction, and here the direction is horizontal. Let's say you have added them together with a flow called source flow. Source flow, it means there is origin, and the flow is coming out from that origin, and the velocity of the flow is in the radial direction. So source flow has only acting component in the radial direction, and as you know, these blue lines are representing the streamlines, and the concentric circles are obviously the velocity potential lines or equipotential lines. So what happens to if you combine these two flow together? So at one place you have a uniform flow, and other place you have a source in which the flow is emanating outward. So you can think of the source flow is just like a positive charge, and whenever you see a positive charge, that always goes out. So or it could be, think of a negative pole of a magnet, so the magnetic field lines always coming out. So either an electric field lines or a magnetic field lines or flow coming out can be thought of as a source flow. So at this point, I mean, I would like you people to what will be an equal to here. So if I just add them together, what will be the resulting diagram? So take a pause here and try to figure out what will be the resulting pattern. You know. So you see, let's think of one of the streamline which is coming, and this is another streamline coming. So what will happen? They will cancel at some point. So this is streamline from uniform flow in the streamline which is coming from a source flow. they will combine together, and obviously let's say the magnitude of the two would be the same but is in the opposite direction. So there would be some point where you have the resultant would be zero. Similarly, let's say you can think of, if the source is very weak, if source is quite weak, what will happen? The uniform flow would pass over that, because if source is very weak, so the or strength of the source flow, the value of m, which is actually related with the volume flow rate. So less volume is coming out, so the strength is low. Then what will happen? This uniform flow is powerful, and it will take over this source flow. Or it could be other scenario: uniform flow is weaker and your source flow is stronger. Then the source would emerge out, and it will displace whatever the weak uniform flow is. So it all depends on the magnitude of the uniform flow, or is the strength of the uniform flow and the strength of the source flow. Okay, so just see the result for this is it would be look like this. This streamline is going, but here the source is stopping them. So you can think of one of the streamline here, I have shown it as a black, that would act as a solid body. So you can think of the uniform flow would be passing over the body like that. And this point is actually the point where the source is emanating. And you can see that source is coming out, and since the flow is coming out from that side, so one of the streamline would act as a solid body, and you can think of the superposition of these basic plane flows would be a situation in which you have a half shaped body, and the flow over the body is taking place. So and this point would be where two velocities, uniform velocity and the velocity coming from the radial direction in the source flow, would cancel out together. So that point would be called as an stagnation point, and we will do the mathematics later today. So but the superposition of the basic flow result into another flow, and we can easily work out, we know the stream functions of both basic plane flows, so we can easily work out the stream functions for the resulting flow pattern, which is actually a superposition of the basic flows. Okay, let's look at another example. You have a sink flow. Sink flow means looks like the same as source, but instead of going out, it is coming in. So you can think of a negative charge where south pole of the magnet, where field lines are coming in. So if you add them together with a vertex flow, so this time the vertex flow is something like their streamlines are concentric circles. So the color, the blue lines are in both cases representing the streamlines. So can you figure out its resulting pattern? I mean, here also I would like you to draw the resulting pattern. First take the pause here. Okay, so the resulting pattern, I show you the answer here. That would be sort of an spiral flow. So you see, from sink flow, the streamlines are coming to the center, and here the streamlines are in an anti-clockwise direction. So at some point, both streamlines would superimpose together, or what you call it a constructive. In interference in physics, sometimes you have both are superimposing each other, adding them together, so you have a constructive interference, and some point where they're cancelling out. So here in this shape, both streamlines would be superimposing each other, they would be complementing each other. And similarly here there would be some cancellation, because here the streamlines would be in this direction, and here there's some point they would be cancelling out, some point they would be complementing each other. So this would be the sort of spiral flow would be the resulting pattern. Okay, now let's move into a particular resulting pattern generated by combining the two basic flows. Let's say at one point we have placed a source, and plus m is actually the strength of the source. Source is something which is coming out, and at some distance a we have placed another basic potential flow, that is sink. So sink, the strength of the sink would be minus m. So what will happen if you bring the source and sink close together? So what we call it a doublet. Doublet is a resulting pattern which you are going to draw if sink and a source of equal strength brought together. And brought together means just making sure that the distance between them is approaching towards zero. So this source and this source are brought very much close together. And what you're doing is you are bringing together in such a way that the product of their strength and the distance between them remains constant. So their strength is m, and if you multiply by the distance between them, let's say if it is a, or if I think I should take it as 2a basically. Okay, we will see it the geometry later, but what will be the resulting pattern? I mean the source and sink combined together. So just take it a pause and try to find out what will be the resulting pattern if the source and sink combine together in such a manner that the distance between them is approaching towards zero. And not zero, I mean they are brought close. When they brought close together, it means distance is approaching zero, but you are making sure that the product of their strength and the distance remains constant. And then the resulting pattern would be given a name called doublet. So this would be your doublet. So here source is coming out, so that is coming out, and here sink is going in, sink is going in. So this would be one of the streamline, this is another streamline, this would be another streamline on the positive y direction, and similarly you would have source is outward and sink is inward. So this would be the resulting pattern. And actually I must say the distance between them is 2a, that's why this equation says 2a. So think of 2 here. So because from the origin to the source the distance is a, so the total distance would be 2a here. So I have actually just mentioned 2a here, and that is what I have written in the mathematical equation. So this mathematical equation is just the mathematical form of this statement. What we are doing is a is approaching towards zero. So from this distance to this distance is approaching towards zero in such a manner that the product of the distance and the strength of the source or sink, because they are of equal strength, so it would be m. If you take the product and you are bringing them closer, and so the resulting equation would be constant. So if the constant and the streamlines end up with some resulting pattern, this pattern is given a name as doublet. Okay, now let's see more closely when we see its mathematical form. So the same case, I mean now you see the distance is 2a between the source and the sink. So actually the distance from the origin to the sink or the distance from the origin to the source is a. So they are placed from the origin at equal distance and their strength are same. And if you see the nomenclature here, x is Cartesian coordinate system, x and y. So if there is a point in the space, I can say the origin from this place to this place is x distance and y distance. Or if I can specify the same point in a polar coordinate system by means of the radial distance r and this angle theta. So this r and theta or x and y represent the same point P in the space. So we have and r1 is the radial distance for the same point if you took it from your sink, and r2 is the radial distance and theta 2 is the angle if you take it the point from the source. So this is actually the situation. You have origin here, and source and sink are at distance a. So the total distance between the source and sink would be 2a. So what you are doing is there is a strength of the source, and we know the expression mathematically. The stream function for the doublet would be nothing, just the superposition of the stream functions for source and sink. So if you recall back your previous lecture, we have already worked out m theta would be the stream function for source or sink. So if it is source, then m is positive, otherwise if it is sink, then m would be negative. So what I have done is the stream function for the doublet would be nothing, just adding then the stream function for the source and the sink. So here m is common, so I can say my stream function would be minus m times theta 1 minus theta 2. So I have taken deliberately m common, so minus m with theta 2 it would be minus m. So if you multiply minus m theta 1 minus minus plus m times theta 2, I get the same expression. So wherever you take some common, always do this, first check it out. If you multiplying them together, are you getting the same thing or not? I mean, that is always handy in problem solving as well. So okay, you can bring psi and m to the left hand side and theta 1 minus theta 2 on the right hand side. Okay, the next what I do is if I am interested in, if I have just taken tangent on both sides of this equation, so tangent of psi over minus m and tangent of theta 1 minus theta 2. So okay, the next is to work out the expression for tangent of theta 1 and theta 2. So from your knowledge of second year or first year, I don't know, first year trigonometry, you know tangent of theta 1 has a formula, tangent of theta 1 minus tangent of theta 2, 1 plus tangent of theta 1 and tangent of theta 2. Okay, at this point we can from the geometry we can easily work out the expression of tangent of theta 1 and tangent of theta 2. So just look at first for a tangent of theta 1. So tangent of theta means 1 means perpendicular over base. So perpendicular would be how much? This vertical distance. So if I say if it is r, if it is theta, so r sine theta would be the vertical distance and r cos theta would be the horizontal distance. So if it is r, then this distance would be r sine theta and this horizontal distance would be r cos theta. If you draw a perpendicular from the point P to the horizontal axis, so this distance would be r cos theta and this distance would be r sin theta. So if I need to work out from the geometry, the tangent of theta 1 would be perpendicular distance over the for in terms of theta 1 it would be this distance divided by this distance. So this distance is r cos theta minus a, because the whole distance is r cos theta and this distance is a. So from this point to this point, that would be r cos theta minus a. So that is how you have worked out tangent of theta. Perpendicular distance, which is r sin theta, and r cos theta minus a is the horizontal distance. That would be the expression for tangent of theta 1. Similarly, we can work out the expression for tangent of theta 2. Vertical distance is same as r sin theta, but the horizontal distance from this point to this point, so that would be something like r cos theta is the whole distance and plus a is added. So that would be the expression for tangent of theta. Now we have expression for tangent of theta 1 and tangent of theta 2. I can substitute back here to get my expression for tangent of minus psi over m. So just substitute tangent of theta 1 and theta 2 in this equation and simplify. So you end up with this expression. Okay, psi, if you are interested in the corresponding stream function, so psi would be minus m times tangent inverse of this thing. So that would allow us to work out the expression for the stream function for this resulting pattern. We have given a name doublet. Okay, So here this psi would be minus m times tangent inverse of the term in the bracket. Okay, we can easily work out because we know the definition for doublet is when the distance between them approaches towards 0. So it is only possible the source and sink brought together so that A becomes approaches towards 0. So if you apply the limit for the term in the bracket, so I put the limit A approaches to 0 and for the term R over R square minus A, forget about right now 2A sine theta. So you have just taken care of the limit, then this limit would bring, if you solve this limit from your first year calculus, so you end up with 1 upon R. So that would be 1 upon R because A approaches 0. So R and R cancel out, so you get 1 upon R. Okay, so eventually minus M and 2A because 2A is a constant, so you take out from that inverse because it is inverse of something. So sine theta over R is there. So that would be your corresponding stream function. Since M and 2A it is a product which is a constant, so this constant is actually called the strength of the doublet. So more the strength of the source or sink, obviously, because they are of equal strength, and if you multiply by the distance between the source and sink, you will be able to get the constant K, which is actually called as strength of the doublet. And this is the stream function we have written in terms of polar coordinate system, and we can write it down by just mathematical manipulation. I just multiply and divide by R, the same expression, so then denominator becomes R square and R sine theta. So you know when it is R and it is theta, and this is X, this is Y. So Y would be R cos theta and X, Y would be R sine theta and X would be R cos theta. So here you have R sine theta, so it would be Y. Y would be R sine theta, and obviously R square would be X square plus Y square. If this is X, this is Y, then it would be X square plus Y square would be R square, or R would be under root X square plus Y square. So eventually we got the stream function for the doublet, which is the resulting pattern, and X, Y are the position in the space. If you know that, you can easily work out the stream function any point in the space. Okay, similarly, as we have worked out stream function, we know that the stream functions, if you know that have a knowledge of stream functions, you can work out the radial component and tangential component. Similarly, for velocity potential function also you have the relationship. So if you look at the source flows, if VR is this and VR is this, if both are same, what we can say here is, we can say that dava phi by dava r would be the same as 1 upon r dava psi by dava theta. So if you have a knowledge of stream function, you can easily work out velocity potential function. Okay, so what I have done is 1 upon r, I have just differentiated psi with respect to theta. K is a constant, R is a constant because I am differentiating psi with respect to theta. So derivative of sine theta would be cos theta here. So that is what I have the derivative, I have put in the bracket, and very simple I got it because here phi can be worked out if we integrated with respect to r. So k and cos theta are the constant, so you have to integrate r to the power minus 2, and then this integral would be minus 1 over r, and so you simply got it k cos theta minus minus plus and divided by r. So that would be the corresponding velocity potential function for this doublet, and this would be the both doublets. These are streamlines. So these circles are actually the streamlines on the y-axis as well as on the negative y-axis, and the dashed lines are representing the velocity potential lines. So that is represented by that function, and you can substitute back into divided by r, multiply and divide by r, and you can write in by yourself in the Cartesian coordinate system. So what we have done is we have done doublet, we have worked out its corresponding stream function, and we have worked out its velocity potential function, and we can plot both set of streamlines, family of streamlines, and family of velocity potential lines, and eventually we will be able to get flow net. Okay, velocity component. Okay, if you have a knowledge of and you see how we have worked out the stream functions, how we have worked out the velocity potential functions, and the next thing is to work out the velocity component Vr and V theta. So they are simple, just because if you have psi and knowledge of phi, Vr and V theta can be worked out either from stream function or from velocity potential functions. Let's say velocity component we need to work out for doublet. Our velocity component in the radial direction would be 1 upon r dava psi over dava theta. So I have to differentiate psi with respect to theta. So 1 upon r is there, derivative of sin theta would be cos theta. So this would be the velocity component in the radial direction. Similarly, I can work out the velocity component in the tangential direction. And then if I know both the components, I can work out their resultant, because the magnitude of the velocity at any point p in the space for the resulting flow pattern we have given a name doublet would be the just add them together, because cos square theta plus sin square theta is 1. So eventually you get the magnitude of that doublet would be magnitude of the velocity would be k over r square. So more the strength of this doublet, more would be its velocity, so at a given radius. Okay, so this is how you can represent the velocity component in the radial direction and the velocity component in the tangential direction, and this would be the resultant velocity. So okay, the next thing is, actually we have already seen qualitatively, when you combine a source with a combining a source with a uniform flow, the resulting pattern is the flow over a half body. So the same nomenclature I have used. The source is placed at the origin, and any point in the space is represented by coordinates r and theta, and the distance between the source and the stagnation point is actually b here. So you see the velocity, uniform velocity is coming from this place, source is coming from this place, so both velocities cancels out together, so there would be no velocity here. So that point would be called as stagnation point. And where it is located from the origin, if you see this would be the origin is x axis, and here theta is 0. So as you move theta 0, theta 90, and theta 180. So when you move to this point, your theta is 180 here. Okay, so we will work out so many things, how much would be the width of this half body, and we will work out the expression for that streamline which act as a solid body, and that would be the streamlines which is actually passing through that stagnation point as well. So we will be able to work out the mathematical expression of this stream function. So the blue lines would be representing, because obviously from the source inside this inside this surface, which is actually one of the streamline which act as a solid body. So flow is taking place out over the surface of the half body. So there is no meaning of the flow within this body. So that is shown here in the black. So the flow is something like that. You have a stagnation point, and the streamlines are such that it passes over the body. So we can easily work out what will be the velocity when it passes, what will be the pressure here, all these things we can work out. So mathematically the life is simple. The corresponding stream function would be just combining the stream function for the uniform flow, and combining the stream function with the source flow. And we know the mathematical expressions from the basic potential flow, so we just add them together. So u infinity r sine theta would be the expression for if theta is 0, then it would be horizontal. Only u infinity is there, and this would be the stream function for the source flow m times theta. What I have done next, similarly we can work out the corresponding stream function for velocity potential function. That is the velocity potential function for uniform flow, and that is the velocity potential function for source flow. So this is an advantage of superposition of principle, that when you combine these basic plane flows, you end up with the resulting pattern, and the stream functions and velocity potential functions are nothing, just the algebraic sum of those corresponding stream functions as well as for velocity potential functions. Okay, now let's look more closely how much is this distance b is, and how to work out that. So at that stagnation point, we know the u infinity is balanced out with Vr. Vr is the velocity, radial component of velocity in the source flow. So at a stagnation point, what I do is I say physically the u infinity part, which is the speed of the uniform flow, and the velocity of the radial component balances out, and r is b is assumed the distance at which this equation holds. So I just have to balance out these two velocity component, and the distance from the origin where this takes place would be labeled as b. Okay, so from source flow we know that the expression for the radial component of velocity is m over r. So this m over r should be equal to u infinity. So what I say is m over r, but r is changed to b, because when these two velocities are equal, r equals to b. So instead of r, I have just substituted b, so m upon b would be the same as u infinity. And this is very interesting. So I have an expression for b. So where this b should be located, it all depends upon the magnitude of the strength of the source and the magnitude of the free stream velocity, so that uniform velocity. So let's say if b can be worked out as m over u infinity. So b would be 1 unit if m and u infinity are of same strength, and this distance b is being determined by the ratio of m over u infinity. Or other way around, let's say if we have a knowledge of the stagnation point and we want to make it fixed, and we fix the magnitude of the free stream velocity, so what should be the strength of the source? That is something I can work out multiplying this distance with the magnitude of the uniform velocity. I will be able to get the magnitude of the strength of the source I should pick, so that my stagnation point would lie at a distance b from the origin. Okay, this is the next is I can easily work out the expression for the stagnation, this streamline which is passing through the stagnation point, or the streamlines which act as a solid body. So in this equation, what I have done is I have substituted r equals to b and theta equals to 180, because theta is in radian, so pi would be 180. So when I just substituted r equals to b and theta equals to pi, I end up with the expression for an stream function which is passing through the stagnation point, or that streamline which act as a solid body. Okay, as you work out, sine of 180 is what? 0. So you end up with a simple equation m times pi. M times pi would be the expression for an m is b times u infinity. So if I substitute it back, so that would be the stream function for that streamline which is passing through the stagnation point and which act as a solid body. So I have an expression which is somewhat depending on the distance, depending on the magnitude of the speed, and pi. So if I have the knowledge of this and I can easily work out the corresponding stream function. Okay, so this equation is passing through the stagnation point, and which is actually mathematically this equation is representing the contour of this half body, or equation of the contour of this half body. Okay, so psi is your stream function for a half body, where it is a source flow and it is a uniform flow. Okay, what I have done here is this stream function I have put it what I have evaluated for contour of the half body. So u infinity r sine theta plus b m is b times u infinity. So here I simplify this expression because u infinity is common, cancels out. So you end up with this simple mathematical expression r equals to pi b minus. So r would be that radial distance where you are actually end up with this equation of the stream contour of that half body. So and obviously in the flow the streamlines are like that, so there is no singularity because singularity is in the source flow when r approaches 0. So there is no singularity in the flow field over the half body, and I multiply r sine theta. So r sine theta would be the same as, because b is common, it would be b times pi minus theta, same expression rewritten. And as you know from your coordinate system knowledge, y equals to r sine theta. So r sine theta would be y would be b times pi minus theta. So that would be the value of y at the contour of the half body. So as you know, when theta is 0, when you put theta 0, so it would be y equals to pi b, and if you put theta equals to 2 pi, so pi minus 2y would be minus pi b. So the width of the half body would be between plus pi b and minus pi b. So that is what we can see it in this in this diagram too, because that is shown here as well. So you see pi b plus pi b and minus pi b is actually the width. So add them together, it would be 2 pi b is actually the width of the half body. This is something we have worked out at this place. Okay, so width of the half body would be half width would be pi b, so the total width would be 2 pi b. Okay, next we can easily work out the magnitude of the velocity component in the radial direction and in the tangential direction for the resulting flow pattern, that is the flow over a half body. So we are just differentiating psi with respect to theta. I got it because I have just differentiated with respect to theta. So 1 upon r is there. So if you differentiate r is already there, r cancel out. So you have u infinity, derivative of sine theta would be cos theta. Similarly, the differentiate psi with respect to theta. With respect to theta would be m. So since r is there, it would be m over r. Similarly, we can work out the tangential component of the velocity. So the resultant would be the square of the radial component and the square of the tangential component. If you add them together, you will be able to get the magnitude of the velocity. So v r, this thing, plus v theta, I have just add them together and simplify so that I got the magnitude of the velocity. So my magnitude of velocity is this thing. U infinity square, it depends on the distance from the stagnation point at any position in the space. If you just substitute different values of r and theta, you are going to get the magnitude of that velocity. So r and theta is just the input required to get the magnitude of the velocity. Since this is an inviscid flow takes place over a half body, so if I have worked out the velocities, I can easily work out the pressures. because I have applied, let's say in the free stream condition, the pressure is P infinity and the velocity is half rho U infinity square. So at any point r theta in the space, pressure would be P and velocity would be V. So this velocity V square, I just substituted here to get this pressure P at any point. So if velocity is known, pressure can be easily worked out from the Bernoulli equation. And we are able to apply the Bernoulli equation because it meets all the conditions. It is an irrotational flow, it is inviscid, it is steady, and it is incompressible. Okay, just see this problem. You have a Rankine body, half body. I mean, sometimes it is called half Rankine body, not Rankine body. Rankine body is a full body actually. It is a half Rankine body or a half body with a thickness of 0.5 meters. So the thickness 2 pi b distance is 0.5. If the body is placed in an air stream with a moving at 20 meters, so uniform speed is 20 meters per second. The question is what source strength is required to simulate the flow. So you need to know what should be the value of M or strength of the source so that you can model this flow. So half width is given here, which is 0.5 meters. So the problem is very simple. As you know, the 2 pi b plus pi b is 0.5, which is given. So pi is a constant, so you can easily work out the distance b. So distance b would be 0.5 over 2 pi. So once you know the distance b, you know the magnitude of the free stream, you can easily work out its corresponding stream function or anything, and you can easily work out the expression for the strength of the source, because b is m over u infinity, or m would be b times u infinity. So b is 0.5 upon 2 pi and multiply by the free stream, so you will be able to get the strength of the source. So if you want b to be 0.5 upon 2 pi, then your source must be of this strength if the uniform flow is taking place at 20 meters per second. Or this problem can be done another way. If you are interested in what should be the speed, if you know the value of b and you know the strength of the source, so you can work out what will be the velocity b, because if you know m, you know b, you can easily work out u infinity. So this is how we can solve such problems, and at this place I end today's lecture.